Hi, in today's lecture, we're going to move to the next section of Atiyah-MacDonald where we discuss operations on ideals. Okay, we'll start with defining sum, product, and intersection, and see a few examples. Same goes for ideal quotients, then radicals, and extension and contraction, which are each defined relative to a homomorphism. We'll start by defining the sum, product, and intersection of ideals. So let's define a ring R, and we'll have cursive A and cursive B inside of R as ideals. Okay, given that setup, the sum will be denoted A plus B. And this is the set of elements of the form A plus B, where A is in A, and you guessed it, B is in B. Okay, and this is an ideal without any further construction, right? You just take any pair of elements and add them up, and that gives you an ideal. You can check this is closed as a subgroup, and multiplying by any element of the ring stays inside of A plus B, given that you have the distributive property. So R times A plus B is equal to RA plus RB. As for the closure as a subgroup, if you have A1 plus B1 plus A2 plus B2, that's obviously A1 plus A2, which is in A, plus B1 plus B2. Okay, so that's works as an ideal. Now let's look at the product. So here we denote it as A times B, okay, just by concatenating the symbols. And this is the set of elements AB, where A is in A and B is in B. But this actually would not be an ideal as defined. So we have to additionally take the ideal that this generates. Okay. So you can see that by observing the fact that, so let's say not an ideal as a set of products. The reason is that given a pair of elements A1, B1 plus A2, B2, you wouldn't necessarily be able to write that as A3, B3. Okay, and you can think of examples easily. For example, in the ideal generated by X and Y, if you want to take its product with itself, you would get X squared plus Y squared. Well, that can't be factored over the reals at least. So that's an example of why we need to take the ideal generated by that set of products. And finally, we have the intersection. Okay, and this is just the set theoretic intersection. And you can see for yourself that this is an ideal. Right, intersection of subgroups is a subgroup. Scaling by R stays in A and also stays in B. Okay. Let's consider how all of these constructions look in the context of the ideals generated by 10 and 12 in the integers. Okay, so let's start with sum. So we have 10 plus 12. So this should be the set of elements of the form 10m plus 12n, where m and n are integers. Okay. Well, this is the same as 2 times 5m plus 6n, where m and n are integers, okay? So clearly this is going to be contained in the ideal generated by 2, because every term has a factor of 2. And in fact, setting m to be equal to 1 or m to be equal to -1 and n to be equal to 1, we get 2. So with m equals -1 and n equal to 1, 2 is in the ideal. And furthermore, 10 plus 12 is contained in the ideal generated by 2, since 2 divides every element of the set. Okay, so that tells me that, in fact, the sum of these two ideals is equal to 2. Okay. How about the product of ideals? So this is going to be the set of, or the ideal generated by elements, each of which is a product of an element from 10 and an element from 12. This is going to be the ideal generated by 120. Okay, since every element picks up a factor of 10 from the first ideal and a factor of 12 from the second ideal, we get 120. Okay, let's actually just write that out a bit. So 10m times 12n, where m and n are in z, this gives us 120 mn, where m and n are in z. Okay, and if you take m to be 1, this is clearly just the ideal generated by 120. Okay. Now let's consider the intersection. So 10 intersect 12. Well, we're looking for the set of elements which is in both 10 and 12. So this is the set of n, n in z, such that 10 divides z, n and 12 divides n. Okay, well, if both 10 and 12 divide n, that means that, so we know that n has to have a factor of 4. It also has to have a factor of 3 and 5. Okay, but once it has a factor of 4, that we don't need that extra 2 from 10. So it's enough to say that 60 divides n. Okay, so this is the ideal generated by 60. Okay, what about general rule? So in general, if you want to take the sum of m plus n, this is going to be generated by the GCD of m and n. Okay, and that's what we saw up here. 12 and 10 have greatest common divisor 2, and that's the generator of their sum. If we take the product of m and n, we will get the ideal generated by their product. That's what we saw with 12 and 10 giving 120. And the intersection of m and n will be generated by the least common multiple of m and n, which can also be written as m times n divided by their greatest common divisor. Okay. And in our case, that was, so if m and n are 12 and 10, that would be 120 over 2, or 60. Okay, and that's what we saw when we did the computation. Okay, let's check out how this would work in the context of a polynomial ring. So we'll start with the sum. So x squared y plus xz as an ideal of the polynomial ring in 3 variables, well, I know this will be of the form, so ax squared plus by plus cx plus dz, where a, b, c, and d are polynomials. Okay, but I could actually get ax squared from cx just by setting c to be equal to ax. So I can drop this, I can drop that first term and just have this as generated by x, y, and z. Okay, and you can check that this is the correct ideal by translating from one formulation to the other, and showing that all elements can be expressed in either way. How about the product? So here we have x squared y times xz. This is going to be equal to the set, or rather to the ideal generated by the set of elements of the form ax squared plus by times cx plus dz, where, again, these are all polynomials. Okay, so what does this look like if I wanted to get a minimal set of generators? So I'm going to take some subsets of these variables to be 0. So if I start by fixing b and d to be 0, I'll get x cubed. If I fix a and d to be 0, I'll get xy. B and c to be 0, I'll get x squared z. Then what's next? B and a and c will give me yz. Okay. And you can check that this is a set of generators for the product ideal. Finally, the intersection. Okay, we're going to want polynomials that are in both x squared y and xz. You know what, let's do this on the next slide. Because we're looking at monomial ideals, it's enough to look at the set of monomials that would be contained in the intersection. Okay, so which monomials would be in both of these ideals? Well, if I'm a monomial in either of these ideals, I need to have one of the generators as a factor. So again, this is p is in x squared y, and p is in xz. So if p is in x squared y, that means either x squared divides p or y divides. Again, we're looking at just the set of monomials for now. So if x squared divides p or y divides p, okay, that's from the first fact. But I also need that that p is in xz, which means either x divides p or z divides p. Well, if x squared divides p, then I know that x also divides p, so it's also in the second ideal. So x squared will be a generator. But if y divides p, I'm not yet in this ideal, so I'm going to need one of x or z to divide p. So then I'm going to write either xy divides p or yz divides p, okay, then in either of those cases, we have p being a member of both of those ideals. Okay, so these are the set of generating monomials of this intersection. So our intersection is x squared, xy, yz. Let's compare this to our product. We had xy and yz in the product as well, but we didn't have x squared. Instead, we had x cubed and x squared z, because it wasn't enough to use the fact that x squared, that x is already a factor of x squared. You have to combine the factor from x and x squared together, or from z and x squared. Okay, cool. So things get a little more complicated operating on ideals when we're not in a principal ideal domain like the integers, as you would expect. Okay, now let's define the ideal quotient. So let's take a ring, and let's have A and B inside of R be ideals. Okay, we're going to define the ideal quotient, not to be confused with a quotient ring. The ideal quotient is the set of elements of your ring, X in R, such that X times B is contained in A. Okay. So clearly A, let's write that as a note. Note, A must be contained in the ideal quotient of A by B, because if I have something in the ideal A, whatever I multiply by, I have to be able to stay in A by virtue of the ideal property. But it could be strictly larger. And let's see this at work. Okay, so we have 12, the ideal quotient of 12 by 10. So let's unpack the definition. 12 colon 10. This is the set of A and Z such that 10A is contained in 12. Or rather, the ideal A times 10 is contained in 12, though that's equivalent. Okay, well, what would that need to be? So if 10m times A is equal to 12n, that means that for some n, so let's put it this way. For any m exists n such that 10m times A equals 12n, then that tells us that 5am equal to 6n. Okay. So just taking m to be 1, in order for this to work, we need A to be a multiple of 6. Okay, so that tells us that 12 ideal quotient with 10 should be equal to 6. And as a general rule, if we take m ideal quotient n, what we're going to get is the ideal generated by m divided by the greatest common divisor of m and n. Okay, so here the greatest common divisor was 2, and so you divide 12 by 2, and you get the ideal generated by 6. Okay, let's look at another example, this time a polynomial one. So xz, the ideal generated by xz and yz, quotient with the ideal generated by z, this should be the set of polynomials in C adjoin xyz such that p times the ideal generated by z is contained in the ideal generated by xz and yz. Okay, well, in order to be in that ideal, I need to be able to be expressed p such that p times az, so taking a general element of z, of the ideal generated by z, this should be equal to bxz plus cyz. Okay. And this means for any a, there exists b and c. Okay. So how can we unpack this? Well, if PAZ equals BXZ plus CYZ, we can factor Z out of both sides of that equation. Set of P such that PA equals BX plus CY. Okay, so this is saying that whatever multiple of P you're going to get, it can be expressed as a polynomial linear combination of x and y, which means that this is the ideal generated by x and y. Okay. So kind of nicely, we have this factor shared between the two generators of the original ideal. When we quotient out by the ideal that generates, it falls away, and we're left with the ideal xy. Okay. Using the ideal quotient, we can define the annihilator. Okay, so if we have the ideal generated by 0, and we take the quotient by the ideal generated by x, we have what we define as the annihilator of x. Okay, and written as an x, read as the annihilator of x. Okay, and it's defined in the same way as the ideal quotient. It's the set of A in R such that A times x is contained in the 0 ideal. In other words, A in R such that AX equals 0. Okay. If we want to know what the set of 0 divisors of our ring looks like, one way to do that is just to take the union of all the annihilators. So if you take an of x, if we take for union over x in R of n of x, we get the set of all 0 divisors of R. Okay, let's look at an example. We'll take the ring Z mod 12Z. Okay, and we'll go element by element. Oh, I should actually, there's a key point here. We're going to take x to be not equal to 0. Okay, if you take the annihilator of 0, you're just going to get the whole ring. Okay, so let's go element by element with Z mod 12Z. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 corresponds to 0. Okay, so now we're going to look at the annihilators. Okay, so what do you multiply by 1 to get 0 in this ring? Well, you would have to be, to get a multiple of 12 out of 1, you would need 12. So that's just going to be 0. 2, if you multiply that by 6, you get 12. So we're going to add that in. So this is 0 and 6. How about 3? Well, if we have 0, we can also use 4 to get 12. But similarly, anything with a factor of 4, so 8 also works. Okay, how about 4? Well, we would need a multiple of 3 to get up to 12, so we have a few of those. How about 5? 5 is relatively prime with 12, so we just get 0. 6, any multiple of 2. 6, 8, 10. And obviously all of these are the representatives in the class of the quotient ring. I'm not talking about the elements of Z, but I'm just skipping drawing all of these bars. Okay, 7, that's also relatively prime, so that's going to get a 0. 8, there we're just missing a factor of, well, it has a factor of 4, so we need a factor of 3. So it's everything like this, just like 4. 9 will have 0, 4, or 8. 10, you need a factor of 6. So it goes like that. And 11 is relatively prime, so we have 0 again. Okay, these are the annihilators of all of the elements of Z mod 12Z. If I want to take their union, I get the set of 0 divisors. So the union of the annihilators of X for X not equal to 0 gives me the set of 0 divisors, which is 0, 2, 3, 4, 6, 8, 9, and 10. Okay, that's just what shows up in all of the cells of the all of the lists of annihilators here. And it's also the anything that has 0 annihilator is what gets left off of this list. Those are the non-zero divisors of the ring. Okay, and there probably should be some comment made about whether or not 0 is a 0 divisor. But for now, let's let it be a 0 divisor. Okay, now let's define the radical ideal. So as before, let R be a ring, and let A in R be an ideal. The radical of A, which is written as R of A, but in modern texts, I think it's generally written with the square root sign, but it's read as the radical of A or rad A. This is defined as the set of elements X in R such that there exists an integer n, positive integer n, such that X to the n is in A. Okay. Using this, we can define n, which is called the nil radical. And this is defined as the idea, I guess this is the radical of the 0 ideal. Okay. In other words, this is the set of elements in your ring such that there's some positive integer power so that X to the n is 0. Okay, so this is the set of nilpotent elements of your ring. Now, one way you can define the radical in terms of the nil radical is you could quotient out by A. So take the canonical quotient. So we're in R. So take map R to R mod A. Okay. And then let's let this map, this homomorphism be called phi. And then let N be the nil radical in R mod A. So take N with respect to R mod A, and then take the preimage of under phi of that nil radical. Then that is the radical of A. Okay? And you convince yourself this works, right? Because so take something whose power is equal to 0 in the quotient ring. Well, in the preimage, that means that its power is not necessarily 0, but it's in the ideal A. But that's exactly what it means to be in the radical. Okay. Now let's look at the ideal generated by 40 in the integers and see how these ideas play out here. So if we want the radical ideal of 40, so this is the set of integers such that there exists a power k such that n to the k is in 40. Okay, well, thinking about the prime factorization of 40, 40 is 8 times 5, so that's 2 cubed times 5. So if I want to be a multiple of 40, I better have a prime factor of 2 and a prime factor of 5. As long as I have one of each, then so certainly raising them to the third power, I'll end up in the ideal generated by 40. So this radical ideal should be the ideal generated by 10. Okay. Generally, for the ring of integers, if you have the radical of some of an ideal generated by a number which can be factored as pi to the ai, where I goes from 1 to n, let's say, then the radical will just be the ideal generated by the product of the pi's. Okay, setting aside the powers. Okay, because you just take the largest power appearing in that factorization, and that gives you an exponent that you can raise your generator to end up in the original ideal. Okay. Let's do the radical of x squared y cubed. So we're computing the radical of x squared y cubed. Again, this is the set of elements f in C adjoin xy such that f to the, there exists an n, with f to the n in this ideal. Okay, well, I can name a few elements in there. So certainly x is in this radical, because if I raise it to the second power, I'll get x squared, which is in there. So x is in the radical ideal. And y is also in the radical ideal. Okay, so that tells me that xy is contained in this radical ideal. How do I know that it's actually the whole thing? Well, one way to show it is that, well, this ideal is maximal. So if you add anything else in, you get the whole ring. But we know that 1 is not in the radical ideal. So 1 is not in this radical ideal, because no matter how many times I raise 1 to a power, no matter what large power I raise it to, I'm not going to end up in the ideal generated by x squared and y cubed. So that tells me that the radical is not the whole ring. Okay, so once I'm not the whole ring, and I contain a maximal ideal, it must mean I'm equal to the maximal ideal. Okay. Now we define our final operations, and that's extension and contraction. And this is going to be phrased in terms of a homomorphism of rings. So let's let f from A to B be a homomorphism of rings. Okay, and let's take A to be an ideal of A and B to be, you guessed it, an ideal of B. Okay, now we can define the following operations. So extension, or sorry, first we'll start with contraction. So contraction is given as f inverse of B. Okay. This is an ideal. Okay, without doing any additional operations to it. And sometimes this is denoted B, C. Okay, so you're contracting that ideal B back along the map and looking at the ideal in the original ring. Okay, so let me clarify that this is contained in A. Okay. As for extension, that goes the other way. So it goes forward along the homomorphism. So we have f of A. This is a subset of B, but it is not an ideal. Okay, so in order to get it to be an ideal, you need to allow it to be scaled by arbitrary elements of B. Okay, so this is going to be taken to be the extension of A upper E, and this is an ideal of B. Okay, cool. So let's consider some ring homomorphism and see how the how ideals are extended or contracted. Okay, so we have a map from Z to Z adjoin I. So these are the integers, and these are the Gaussian integers. And we're taking the obvious injective map. N maps to N. Okay. So, so let's consider what happens when we extend ideals moving along this map. And let's consider in particular the prime ideals. So consider extensions of prime ideals. And it turns out, and this is to derive the details of this requires some significant work. There are a few different cases. The first case is p equals 2. So then the ideal 2, when we extend it along this homomorphism, it becomes a square of the ideal generated by 1 plus I. Okay, just kind of interesting. Why is that the case? Well, 2 is a sum of two squares. It's the sum of 1 squared plus 1 squared. And because in the Gaussian integer, sums of squares can be factored. So this is the same as 1 plus I times 1 minus I. 1 minus I can be written as minus I times 1 plus I. Okay, so both of these elements, 1 plus I and 1 minus I, are found in the ideal generated by 1 plus I. And that's what we get as the extension of the prime 2. Okay, what's the next case? The next case are primes that are congruent to 1 mod 4. Okay. What happens in that case? So an example of this would be 5 or 13. To work through. That gets us, so what happens with that is the ideal generated by P extends to a product of two distinct prime ideals. Okay, so this is in contrast to prime 2, which is a square of a prime ideal. This is a product of two distinct prime ideals. Okay, and this has to do with the ability to write such primes as the sum of two squares. Okay, and what's the last case? We have P congruent to 3 mod 4. Okay, and these are primes like 3 and 7. And these have the distinction of extending to ideals that are generated by the same prime. Okay, so unlike the primes that are 1 mod 4, which factor into two prime ideals, these remain prime in the target ring. So we see that there's many different behaviors for primes even under the same homomorphism. Okay. And with that, we've gone through our list of ideal operations, and I thank you for your attention.